This next section briefly touches on network power dissipation, or power dissipation rather, on a chip. And basically this picture here just sort of shows that the power that's consumed by a chip has been increasing over the years, and this is increasing exponentially because this is a linear scale and this is or logarithmic scale, and this is linear. And basically the idea here would be, it's kind of unheard of to think of a 1000-watt CPU. So power dissipation certainly can be a limiting factor in many systems. Battery weight and battery lifetime are very important for portable devices. Packaging and cooling for tethered devices, and I've mentioned a couple other things. A point down here to why you want to keep power low. Sometimes you're constrained by the fact that users want the power low, so that it might be a product differentiator if your device uses low power. Or on the other hand, it might be that the devices use an awful lot of power. So here's a simple example I took from a Facebook server farm, Lule, edge of the Arctic Circle. It's not online yet, but it's projected to cost 760 million, 28,000 square meters, requiring 120 megawatts. So just to put that in perspective, a fairly large hydro dam on the Winnipeg River system is Seven Sisters, and it's 165 megawatts. And that's targeted to go online 2014. And all of this the cooling requirements and the power requirements here are basically as a consequence of transistor switching, and they're very small devices, as you know. Here's a simple RC model, can also yield some intuition on energy consumption of inverter, which we've looked at before. This is just repeating it again. Here we're looking at the output transitioning from a 0 to a 1, so basically we're charging up the capacitance associated with the output of the inverter as well as the load. And we can go through a simple little equation of disintegrating the power over time from 0 to capital T, where it took that time to charge from 0 to VDD. We'd end up seeing that we have 1/2 VDD squared. Basically we know that half VDD squared is stored on the capacitor, so that means that half of that was dissipated in terms of heat. And the other half VDD squared is going to be dissipated when the pull-down resistor discharges that capacitor. So that would be the 1 to 0 transition on the output. Many other types of power consumption are in addition to dynamic power. I guess this would be considered dynamic power as well, though it's a short circuit current. This device is switching in momentarily both the on and off device on. A subthreshold leakage, that means that the transistor down here is on when this node is high. It's on slightly and it's leaking some current through it. The gate leakage, the actual gate itself can leak, and a diode leakage. So those are reverse bias p-in junctions. And here's some of the issues and sort of their the contribution to the power dissipation. So short circuit current, if you keep the edges fast, that should be less than 10% of the capacitor charging current, so that's not unreasonable. The subthreshold leakage is approaching a major percentage of the active power, though, and the other two are probably a little bit more negligible. Anyway, dynamic power, as you know, is the switching power used to charge up a load capacitance or discharge it for that fact. Basically, you can say the dynamic power is going to be proportional to some activity factor, or equal to some activity factor of the devices or the logic present there, times the clock frequency, and this 1/2 was for half the duty cycle times the capacitance that is seen by the load, and by VDD squared. The static power dissipation is simply just the VDD, which is a power supply, times the off current on those devices. So reducing the dynamic power. Well, we've already looked at some, or mentioned some techniques that can be used. Clock gating, so clock node of inactive logic doesn't switch. Data gating, so that data nodes of inactive logic doesn't switch. Bus encodings to minimize transitions, and balanced logic paths to avoid glitches during setup. So in addition to this, you can always reduce the frequency. That doesn't really save energy because it takes you a little longer to do the operation, but it reduces the amount of heat that you have to dissipate at any point in time. You can reduce the switching capacitance, so that might be careful transistor sizing. Put the small transistors off the critical path, for example, if you don't need them to be super fast. Make smaller ones off the critical path, so that's less capacitance. Tighter layouts, which means sort of good floor planning, and segmented buses and muck structures, so those often would have a buffer on them. Reduce power supply voltage, in which case you may have to lower the frequency as well, but you can lower statically for cells that are off the critical path, and perhaps lower dynamically the power supply voltage for just-in-time type of computation. Reducing the static power dissipation. you can try to increase the length of transistors off the critical path, so that makes them longer, that makes them more resistive, that makes them less leaky. You can use high VT, so that's threshold voltage cells, off the critical path, so they're going to be slower, but they're going to have less power dissipation associated with them, but there's an increased fabrication cost. And then there was a couple others. I'm not too sure what the stacked devices means, but the others to use some power gating, where you basically switch off the power supply to parts of the circuit that you're not operating at that point in time. Here's an example of a clock gating. This particular example isn't all that clear because the gated clock, it looks like it's identical to the system clock, but the idea is it can be enabled for just periods of time when you want this gated clock to be active. And it sort of pointed out the Pentium 4 has hundreds of gated clock domains. Here's another example of reducing power with data gating. So the shifter isn't on all the time, it's on a small portion of the time, and it's selected by this multiplexer here. So basically this multiplexer just throws an AND gate here, which when it's active it'll operate, when it's inactive the shifter won't operate. Here's just a little picture, sort of a trade-off between delay and power. In this particular case it's like an energy delay product. Here's the delay, for example, which as the power supply voltage goes way down, approaching the threshold voltage goes way up, and if the power supply voltage goes up, well, the energy required by the chip goes up. So basically there'd be sort of a sweet spot there where you try to find a reasonable energy delay product. Architectures can certainly reduce power consumption. Here's an example of an 8-bit adder comparator. There are some of the stats about it. I think it was a pretty old technology, but it had some base power reference. And here were two interleaved adder comparator units. They operated half as fast, lower voltage, and had a reduction in the power. One pipelined adder comparator unit again operated at a higher speed, took a little bit more area than the 8-bit adder comparator that was being compared to, 1.3 times the area, for example, but the power was down to 40% of the power required by that guy. And pipeline in parallel then was operating at a lower speed, consuming a lot less energy. And here's an example. I think it was pretty old. It sort of came from 92, but it gave an example of what would happen in that case when people did lay out the adder and comparator and then went to the parallel implementation and then went to the pipeline of a simple data path. And here's a simple little voltage scaling example. I don't think this data out here means too much, but let's say pick some other point along here where, let's say, we're looking at 2 volts. So let's say at 400 megahertz and 2 volts, we're consuming roughly 400 picojoules per cycle. And if we go to 3 volts, that's 1.5 times the voltage has gone up. So we roughly go up 2.25 times the power dissipation, which is what you'd see in that particular case. And this was for slightly more modern stuff than we saw previously. It was a 32-bit RISC processor in a TSMC 180 nanometer ASIC process. And at this point in time, take a small break.